Yes, thank you. Thank you for having me, and thanks for the correlation catch-up, because we're using a lot of correlations, in fact, in our data. So, Gaia, what is Gaia? Gaia is part of the bigger wave of astronomical missions or experiments that are coming. So it was launched in 2013 in December, started operations in mid-2014. And this wave comprises really some of the missions that are going to give petabyte scale data. The biggest one that it's quite extreme is 5 exabyte from a square kilometer array telescope. But in general, we see that databases in astronomy interleave. Also, Jim Gray was mentioned yesterday. He was one of the database guys who was pushing usage of databases in this domain. What is Gaia? What is the goal of the mission? So, first goal of Gaia is to do 3D cartography of the Milky Way, of our galaxy, of additional properties like motion, color, brightness, to do some relatively simple studies like variability that I'm responsible for. And in general, this is census of the galaxy. So we want to catalog our galaxy, to make as most precise and as most accurate catalog of the galaxy. And it sounds simple, but details are a bit complex, as usual. So this is a mission of superlatives, and there is no really competing mission now. NASA had something in works, but it was canceled. So for the next 20, 30 years, we think the data from Gaia will be used by researchers. And we know that we want to understand the galaxy and its history, but also we want to describe fundamental properties of the stars. We have a bigger scale, so it's kind of easier to do these things. We want to calibrate the distances of the universe, so cosmological scales. We want to discover a lot of interesting variable stars like binary, exoplanets, stars with planets, variable stars, supernovas, so kind of transient events, black holes, everything you name it, Gaia has a chance to find. And also we're looking for new phenomena. We want to constrain dark matter, or to help at least to understand what dark matter is. And it's also a base for the next future projects. So LSST friends from LSST are here. So the Gaia catalog is going to be a base for kind of calibration, the startup for bootstrapping of LSST. And I'm very happy to say that our immediate impact, we had the second data release last end of April. It already is the most cited astronomical article. This is just a main article. There's like 10, 20 accompanying articles that were published with the data release. So we have this cyclic operations. Every year, 2 years, we publish the data. And a few examples. So foremost, the easiest to spot is the galactic map of stars. In fact, this is not a picture. This is a drawing that is derived from the data. So you can see here 1.7 billion stars. Of course, this is an approximation, which is 1 or 2% of our galaxy. We don't know really how big galaxy is. This is estimation. We're looking quite deep inside. We see roughly 30,000 light years in all directions. And we can, for example, derive from the data that Gaia produces dust, so extinction maps. This is also interesting for people who are looking deeper. We see, thanks to Gaia, that there is evident signature of the Sagittarius dwarf galaxy. So this finger here, you see, it's kind of cutting our galaxy. Very interesting discovery that was evident just right after the publication of the data release 2 was that we see signatures of the collision with the other galaxy, Enceladus, around 10 billion years ago, so quite deep in the past. And this is one of my favorites. Normally, we expected that because the Milky Way rotates, galaxy rotates, so some of the stars are expelled from the galaxy. But it turned out that a lot of stars are actually coming to us at a very high velocity. So we don't know why. This is just a few examples. As you see, there's over 1,000 publications. So this is really vast number of topics. Okay. And this is spacecraft itself. And it's relatively big. It's 2 tons. It's roughly 10 meters in diameter. This is the shield that opened when it was launched. There's a lot of interesting things about Gaia if it comes to technology itself. So this is the biggest detector. It's 1 gigapixel detector in the sky. So I'm going to show in a moment how it works. But in order to to make this thing work as it was designed. There was a number of technological breakthroughs as well. So what is it? First of all, this is, Gaia is not one telescope, it's two telescopes. So you have two mirrors. You have a number of associated mirrors. It goes down, down, down. And you have the CCD that I showed, the 1 gigapixel CCD. So it's quite long focal length, 10 mirrors inside. There's a very interesting thing about the structure, the torus that it's built on. So let's see small simulation. The torus itself is made from carbon silicon, and it's actually baked. So structurally, it's a single crystal, if you will. This is done so the stability of the temperature of the mirrors is extremely high. Inside there is interferometer, so the angle, which is set here, is measured to the subatomic precision. So we know if the angle is actually good. This is important because we want to know exactly how this angle changes, if it changes. Then we have the payload inside, then we have the shield. The shield is to basically protect us from the sun, but also Gaia is in very peculiar place. For example, the precision of Gaia could be shown as a capability of seeing basically €1 or $0.25 on the moon. So this is this kind of precision of resolution we're talking about. It took some time to get to the L2 orbit, so this is special Lissajous orbit, where we have balance between the sun and the Earth. So it's quasi-stable. There's never eclipse there. So we don't call Gaia normally satellite because it's actually orbiting with the Earth. It never orbits around the Earth. It's orbiting with the Earth around the sun. And the downlink is not that fast, so there's a lot of compression going on. There's, for example, phase array antennas used for the first time, so like GSM antennas to transmit data on the Earth and so on. Okay. Scanning low. So Gaia rotates. Gaia is moving. It has a very peculiar movement. It's this far away, this million miles away, and it's rotating super stable way. There are 12 thrusters. Some of the thrusters have power of the B, more or less, to keep it in super precise movement. When it's moving, it's scanning the sky. So every 6 months, we scan the sky. Every 100 minutes, we have a chance to see the same star. And every year, we see sky twice. But it's not really uniform. This is very important, the scanning law, because it defines what we can see. So let's have a look what happens really when the light goes into Gaia. So let's imagine, first of all, we have star mappers. Star mappers are responsible to discern which mirror is really the light coming from. Then we have the CCDs. From each CCD, we get the data down from the gates. Then we have the spectrometers, BPRP, so blue and red. And then we have radial velocity that basically check how fast the objects are moving away or towards us. It takes roughly 45 seconds to scan the whole plane. And we have thousands of the stars basically being tracked at any time. So what Gaia does is not really making pictures, I would imagine, because we have no capability to transfer all this data. The downlink is too slow, even if it's super modern for astronomy at least. Oh, again, sorry. But what we have is really the pieces of the data. These are basically PDFs. So the functions that tell you about the density. And this is what we download. This is the data that we download. The rest is done by the satellite, by the spacecraft. It's kind of Internet of Things processing in the space. So a lot of processing is done there. There are VPUs and so on. And because of this peculiar movement, Gaia gives quite peculiar scanning law. Scanning law is the way we see the sky. So here, this is animation showing first the stars. So we see the first field of view, the second field of view. This is where Gaia is, and this is the time. So first you can see over hours how it scans the sky. It's getting slow. It's gradually moving, changing the angle. And then you have some increase after 1 day, so you have 2 days. And then it accelerates. Over days, it looks like this. So You see, in a few days, you scan part of the sky, but some part of the sky are not scanned until, let's say, half a year. When we have the whole sky. But still, the number of points, the number of transitions, it's not that high in certain points. There are points that are saturated with measurements, which is super nice. But there are points that are quasi-empty or very small. So this kind of already shows the intrinsic problem of the data that we have. The time series sparsity, if we deal with time series derived from the scanning law, some of the time series will look very funny. We'll have 2 points and then nothing. Or 2 points after half a year, we have another 2 points in some extreme cases after, let's say, 1 year or 2 years. So how we do this? So Gaia is a European mission, so there are 6 data processing centers. I'm representing Geneva here, but there's a number of them. The real center with the kind of, which is Data Hub, is in Spain. So this is Spain, this is ESAC, and which is also the hub for all the data. So mission control sends the data to ESAC, to Madrid, and Madrid is responsible to distribute this data to subsequent data processing centers. And each processing center has some coordination unit, call them. So it's basically scientific work that does the data processing, data analysis. We are quite at the end of the food chain for the data, so I'm showing this kind of in order, what's happening. For example, Barcelona is using roughly 170,000 cores for several weeks to just do the mapping, because the transit I showed you is kind of anonymous. You have to map it to the star. So it's quite complicated procedure, and it's really super compute intensive. So when the data comes to us, it's already processed by all these DPCs. There's also Cambridge that does calibration, photometric calibration. And then there are other CUs that do some specific studies. And in Geneva, we're responsible for variability studies. So this is what I'm going to talk about now. In general, the data processing consortium is around 450 people. I think total number is 600 that have been involved. In Geneva, we around 10, but we coordinate 45 people in total. So the data that it's kind of being circulated through this hub is in our binary format, Gaia format. This is distributed via Aspera, although from my perspective, the BitTorrent will be much better choice, because we basically have publish, subscribe distribution of the data. For many people, this is really life achievement, so 2 decades. So if there are people who still work from the beginning, so this is something really special. And DPCs are independent, so there is some level of homogeneity that we expected to have. For example, Java should be the language of the pipeline. Also, all the code will be open source at the end of the mission, which is 2022 probably. And also the data, as I mentioned already, the data public release. So this is what we do. We publish the data, so it's really accessible to everybody. You can just Google Gaia data release, and you get the link to the archive. I mentioned this is the publish subscribe paradigm, how the data is exchanged between the DPCs. And this is the main tool that basically defines what is exchanged. So let's say this is my coordination unit with the variability. We have some classes defined. They are defined in this tool with the fields, with the specific description, with the specific types. The types could be complex. And then if somebody is interested, they subscribe. They say, I'm interested in this type. I'm, for example, CU4, CU8 from DPCC, from Toulouse, from France, said, OK, we're interested in this type, so this is source result. We subscribe. What it means that anytime we publish something that goes to Madrid, they will get it sometimes after. And this is all or nothing, so you cannot say, I would be interested in this specific types that have this variability level. No, you just get everything. So it's up to you then to filter this and process it. Cycles. In order not to have people waiting till the end of the mission, we have these cyclic operations, and they have 1 year, 2 years, but internally you have much less time to process. So with increasingly bigger amounts of data. For example, for us, it's usually between 3-4 months to 6-7 months per processing per cycle. Now we're getting to the cycle 3. So you see there is like 30% more of data that we're going to get. And there's also possibility of the extension of the mission because we are quite lucky with the spacecraft. The sun was very silent last few years. So normally this mission was designed to run for 5 years, but because the sun is quite calm, we may run for longer. Also, just to say that, for example, events like flares on the sun could degrade the time of the mission of 1 day for a year. So if we have a flare, you just deduct 1 year of the mission because the impact is so high on the silicon inside, mostly CCDs. Variability studies. So this is what we do. This is kind of simplification of what we think when we say variability stars. So you can think of this as kind of biological Linnaeus tree of the species, but some of the species are quite overlapping. So you could have eruptive, and you could have eclipse. You could have rotation. You could have, for example, eclipsing binaries that are eruptive, that are pulsating, and so on. So you can mix these types. But just to give you an idea that we're dealing with like roughly 30 types. So Gaia, from my perspective, our perspective, is classification problem or characterization more problem, because we're not only interested in classifying these stars, so just getting, deciding if you look at some time series which is photometric data. Is it cataclysmic? Is it eruptive? Is it ecliptic? If it's periodic, for example. So then when you know what it is, you try to derive some characteristics of the star. So some more special fine-tuned information. If it's pulsating, how many pulses it has, is it type 1, type B, and so on. So also we were looking for the discovery of the new types. So this kind of already tells you that this is both supervised classification problem and unsupervised classification problem, or discovery problem. So how to look at the data. And just to put some perspective of the impact, these are existing catalogs, the variable catalogs. OGLE is the biggest one, so it's around 1 million stars. Our data release 2 was 500,000. In fact, we were not supposed to be part of DR1 and DR2, but we decided to learn by doing. So normally we should start here, but this was a very good choice. We learned a lot, what to do, what not to do. And the next data release, we aim at 10 million. So already you see this is the kind of tenfold increase. Then we going to, let's say, 10–15% of variables that we think of all the stars. So we're talking about 150 to 100 million variables. And this is really changing the landscape, what you can do with this data, with the results. So I'll try to make it quick description of how the workflow looks like from the operational perspective. So first we're getting these files from Madrid. This is roughly 1 million files. Of course, they don't come over 1 day. It takes a few weeks to transfer. Then we have a system specially made for parallel ingestion. We got roughly 3 to 5 terabytes per hour. This is quasi-compressed, so the real I/O may be a bit lower. Then we have automatic schema mapping. Once we have the file, we can just get the file. I've showed you this tool for the type subscriptions. So we just get the file that it's generated according to the dictionary, this data dictionary, and we automatically can generate the schema in database for this file. And then we load it. So we have roughly 30 tables like this for the input, 2.5 billion sources, hundreds of billions of transits, and trillions of values, really. Then the next step, we are different than the rest of the consortium. We need time series. What we get is really a flow of transits, right? They are associated with the source IDs, but they're not ordered in any really meaningful way. So we have to do basically group by, order by time. This is what really happens. And we derive time series. So it takes 24, 72 hours for the basic photometry. Spectra is really 80% of the data. And we don't plan right now to use all the spectra. So spectra is kind of done, the time series reconstruction is done on the fly. If the API is asking for a spectra, we do reconstruction of the time series on the fly. And then there's quite interesting and important part, which is the cross-matching of literature and previous cycles. What does it mean? We create catalogs. So catalogs are projections of the sources that we get. We organize the sources in some kind of way that give us a hook on reality. So reality is the literature and our previous results. And also we do sampling. So we have some catalogs of the samples. We have roughly 200 catalogs. And in the end, we have a hierarchy of the catalogs. So just by the names you can derive, this is the size of the catalog. Some catalogs are owning, so they really define the identity of the source, because we could have different, not only Gaia. We started before, so we had to do also to deal with other surveys. And then you have a number of other catalogs. There's also, and this is important, attributes. We have to import the attributes from other catalogs from literature to actually derive, to make a comparison. For example, we could do classifier based on the literature catalog, and then compare if the attributes that we derived from Gaia also give similar results if we train the classifier. Then once we have the catalogs, we do outlier analysis. So what it is, this is the time series I mentioned before. So we have G, BP, RP. So this is visible, like main band. This is blue, this is red. And this is CCD. So I remember this single CCDs that we're giving the data. For a number of the sources, we have access to this. And then right after we received the data for the first time, it was clear that the time series is not totally, but quite a junk. You have a lot of junk there. There's full of noise. There are some artifacts nobody expected. Even the mission was in preparation for years. There were simulations for years. The simulations didn't give you the idea what real kind of problems are there. So what we decided to do is we invented the notion of time series operator. Operators are pieces of code plus configuration that clean the time series. Then we have a derived time series. So these are the names. We have the whole chain of them. We don't store this time series in the system. They are transient. But we store results associated with this time series. Let's have a look how it happens. So when we want to prepare, let's say, one operator, which is quite clear what it means, right? Remove outliers, faint and bright. So both on the bright end and the faint end. We have to have some statistical tools to do this. So here, let's say we have number of plots. We choose one plot. This plot is log error versus magnitude. And this is important where we needed a sample. In order for scientists to operate, to derive this data, we have to have some sample that is workable on a small machine, because you want to do this many times, you want to do this fast, and so on. So here we derived some, let's say we choose this line to cut off all these things that are here. We choose this line to cut off these things here. We put it in configuration, we run. Why we need this? This is just example. This is skewness with kind of standard outlier removal that we had before. And I think it looks similar, right? This looks like a scanning law, actually. This is not what you expect. You should see something like this. And this is what you see only after you apply the operator. So there's tons and tons and dozens of problems like this to just clean the data. When you clean the data, the rest is relatively pleasant journey. So we have the first runs, we call them. So on the same small catalogs that we prepared, we run the pipeline, and this consists of classification, variability studies, special detection, special object studies. But of course, we have to prepare these things first. And these are pretty small sets, from 1 to 10 million sources. We derived some statistics, some correlations, and so on. And we do this. So let's have a look what from an operational point of view, how it looks like. So we have run. Run is basically defining what algorithm, what version of algorithm, what data, what catalog you're going to use. And you have like several thousands of lines of XML that defines the parameters of your run. So we store, I should say that everything we do is stored in database. We try not to store anything outside of the database, which is quite challenging sometimes, but models, runs, input, output, everything is stored in the database. Then we try we have generations of these and so on. One of the main problems with classification when you deal with kind of heterogeneous data in astronomy and anywhere is that attributes that you have to deal with are different depending on the survey. So we have the kind of special part of the framework that's called attribute mapping, which is again kind of DSL, which extracts for the same names eventually different values. So this is, for example, from Gaia, but you could have like given attribute here, we just give the name of the attribute from the catalog. And what does it mean? This means that you could use the same attribute mapping or the same logical mapping for different inputs. So you don't have to worry about this. You could use the same classifier in the end or train the same classifier. And this is what happens. We first get this attribute mapping, we published, and then we train the classifier. And then again, in classifier, you refer to such an attribute mapping, you define the classifier. So our classifiers could be hierarchical. We started to develop this stuff before this explosion that happened last few years if it comes to the frameworks for the classification. And we are model agnostic, so we could store anything that's storable, we can store and just link it with the configuration file to the specific framework, so we could use it externally. And the number of classifiers is not that big because it really takes a lot of time to create a good classifier. Then you have to analyze this, you have some kind of confusion metrics, and it's quite clear. If it's good, we can go to the main runs. If it's not good, you repeat until it is good. And then you have the first final runs. It's never one. We always say it's one run, but it's never one run. It's a number of runs because something goes bad. But there you have the full input. You put the full catalog, the ONI catalog, and then you run on everything. And then you derive again some statistics, some attributes. We roughly have 500 values as such as if it comes to maybe more, it's around 500,000 because they are arrays. And then we go to validation. So we have a number of dimensions for validation. First of all, we have visualization. So we have metrics that could be easily visualized, like 1D, 2D histograms, sky maps, category histograms. But we also have, again, kind of DSL for validation rules. So this is just a snippet of what a validation rule is. It's basically checking if some of the parameters that we produce make sense. So you say what it is, you say what type it is, and there is some code associated with it. Somewhere it could be Java, could be Groovy, could be expression language, so completely dynamically evaluated. And then you have, of course, technical evaluation. So we have Kibana, Grafana, you name it. And also very important thing is that from this high-level perspective, when you say, let's say you have 1D histogram, quite often it's very important to have a quick access to a specific source or time series. So we have the dashboard or the web tool that does it. So you have sources here, source IDs, and this is some results, and then you can analyze a specific source. So it's important to get from this top-level view to the single source quickly. This is quite important. And then when everything goes well, we export it, we validate again, because when you export, you can also make errors, and then we export to Madrid. So this is a real example, so I'm not going to dive into details, just to show that sometimes we have more than one run, and these runs basically operate on different input, and then you have to merge this input, and this is quite bad. So there are quite complicated use cases, basically coming from the fact that we don't have infinite time to do all these things. So for architecture, there are two requirements. So batch-oriented, I/O should be less than 10% of total processing time. And for analytics and discovery, especially this, drill down, 1 millisecond per source. So we have 1 millisecond source. You have to do some overhead, add some overhead for displaying. And this is what we get. And also that we need kind of flexible framework based on NewSQL, for example. So this is the architecture, quite typical. We have the HPC cluster, which is not that big. It's very small in the comparison to the talks we had. It runs on Apache Camel. We also have some auxiliary kind of frameworks running. We have some also auxiliary services like Dashboard, Mattermost, OnCloud, and so on. And this is the core of what we do. We have coordinator. Coordinator talks to basically spawns the runs. The runs basically run as agents on the cluster. They talk to the database, they store the data, but they also generate a stream of events for this global view. So coordinator, very similar way to Spark, is aggregating them and storing database just for the future checks. And data model is built around HillPix. So just super quick introduction. There are a number of indexing schemes for the Sky. This is one of them. It's very nice because it's nested. So you can just imagine this kind of as a fractal. It's going down. And it's very efficient because it's binary based. So it's easy to make certain things quicker than usual. And when we have this source ID based on HillPix, we can also quite easily do some range partitioning that we also distribute. So we have partition tables that we distribute over a number of nodes. And okay, so it's good. So this is just an example. We have queries that give you the views that I showed you before. It's around 2 to 5 minutes on the cluster. And this is what we run on. So this is PostgreSQL. So almost everybody knows Postgres. The difference is that PostgreSQL has a global transaction manager, so the piece responsible for allowing you to get the transactional IDs, which is distributed or centralized. Then are proxies, number of things. The cool things about the system is that you have access to, you can connect to any coordinator, so any node, and have consistent view of the system. Okay, so I skip this, and yeah, I think future typical. We want to expand and do new things. So, thank you.
Thank you very much, Christoph. We've come a long way from using magnifying glasses on photographic plates, haven't we? Just a little bit, huh? All right, time for just a couple questions. Just one or two questions. Anybody have an urgent question? Besides, when's lunch?
Is your use of PostgreSQL forked, or is it on the main line to get to those sizes?
No, it's in the main line. It's the core, really. We use it.
It's all okay. So there's no forking or customizations you've done. You've just got you haven't forked PostgreSQL.
Yes. So we were looking for something that is something like PostgreSQL. At the time it was called PostgreSQL, and we're quite close to the developers, so I'll slide about it. We basically also looking for people to help us to merge it with Postgres 12, for example. We need allies, so we try to organize, so we're trying to be kind of catalyst for PostgreSQL as well. So if you have any questions about PostgreSQL, I'm happy to answer.
This is why, by the way, it's so important to vote on the lightning talks. Christoph is our winner of the lightning talk from last year, and so he got the invitation to come and do the long version this year.
Too long, sorry.
This is how the voting turns into a really excellent, fascinating talk here. So important to vote on the lightning talks at the end of the session today. All right, lunchtime.
Thank you.
What time are we coming back?
Yeah, so theoretically 1:15, but 25 minutes is kind of short, so we will probably let's start 1:30, and then the 15 minutes that we had scheduled, we can do at the end together with the closing remarks. So we will be back at 1:30. Thank you.